Hi, I am Daniel Tong from George Mason University in Fairfax, Virginia. As a member of the NASA Health and Air Quality Applied Science team, our work focuses on advancing the nation's air quality forecasting with satellite applications. Air quality forecasting is widely used to help local forecasters to determine the air quality conditions of tomorrow and even the day after tomorrow. It's also used to provide time-sensitive information to public health managers and emergency responders during extreme events such as wildfires, dust storms, and volcano eruptions. An air quality forecasting system is like a human working on two legs. One leg is meteorology, the other one is emission. The air quality model can take meteorology and emission as input to generate air pollution concentrations. In this project, we focus on using satellite data to improve the emissions input. We have developed a new technique called the emission data assimilation that simulates a suite of satellite observations to reduce uncertainties in the emission dataset. Next, we are going to provide a few examples how we can use satellite observations to reduce emission uncertainty and improve the data quality to drive air quality forecasting. In the first example, we will demonstrate how to use satellite data to improve anthropogenic emissions. Anthropogenic emissions are usually taken from the National Emission Inventories, or NEIs. Even the latest NEI, however, are several years old, making it impossible to represent the current emission levels for the forecast year. Here we compared the emission trend of nitrogen oxides in the National Forecast Model to that observed by the OMI satellite sensor and AQS ground monitors. Both OMI and AQS showed a consistent decreasing trend that was not reflected in the model emissions. This clearly demonstrates the importance of using observation to rapidly refresh emissions for better forecasting. We have combined the OMI and AQS trend to come up with an adjustment factor for each state, and then use this state level factor to adjust the NEI to drive the air quality forecast model. We used this approach to quantify the impact of the 2008 Great Recession on the U.S. air quality. The recession impact was estimated from the differences between two model runs, one with the business as usual emission, the other one with the recession emission. In the business as usual case, the EPA emission projection from the cross-state air pollution rule, or CASPR, was used to represent the would-be emission level without the recession. In the recession case, the observed emission trend from OMI and AQS were used to represent the actual emission changes. In both cases, surface ozone concentration decreased quite a bit from 2005 to 2011 as a result of decreased emissions. The difference between business as usual and a recession, which is shown at the bottom, showed that the recession has further reduced the ozone concentration in the eastern United States and also in the Pacific West. The ozone concentration actually increased in Southern California due to reduced titration. There was also an increase in central US, which was caused by increased emission from the oil and gas operations in this region. The ongoing COVID-19 pandemic has caused one of the most dramatic emission changes in our recent history. Here we showed the state-level emission changes observed by the AQS and the OMI. The merged adjustment factors are shown on the right panel, compared to our previous work on the recession. This new study is challenging for several reasons. First, the air quality in the United States has improved significantly in the past decade. It imposed actually much higher requirement for the sensors and the retrieval algorithms to observe NO2 changes in a cleaner environment. Second, the satellite and the ground monitors are generally in agreement with each other. However, there are places they are not in agreement. Therefore, it's important to compare notes with different sources to understand the uncertainties in the observations. Finally, for this kind of applications, it's important to have long-term, consistent data record that allowed us to use the emission trend.
The global lockdown due to the COVID-19 pandemic led to widespread reductions in human emissions and resulted in probably the largest natural air pollution control experiment ever. Here at George Mason University and NOAA Air Resources Laboratory, we are using both satellite and ground observations to approximate the change in human emissions due to the COVID-19 lockdown. We are using those emissions as input to the community multi-scale air quality model and are studying the impacts on ground level ozone pollution over the different regions of the United States. The early results shown here, with emission changes on the left and ozone changes on the right from March into April 2020, demonstrate that the COVID-19 impacts on ozone pollution were variable across the US, with both widespread decreases in blue and also localized increases in red. As we look into the later months, we hope to learn a lot about the impacts of widespread emission reductions on air pollution levels and the implications for future public health management.
Hello, my name is Juliana Christopoulos and I'm a rising junior at Cornell University. This summer, I had the opportunity to work as an intern for the National Oceanic and Atmospheric Administration and conduct my own research project under the supervision of Dr. Daniel Tong. The aim of my research is to assess how COVID-19 related emissions changes are affecting soybean crop yields for this year. So far, I've utilized ground level ozone data acquired by the Community Multi-Scale Air Quality Model, or CMAQ for short, to calculate the cumulative exposure indices whose equations are indicated. For 2019, I decided to focus my attention on the summer months, where soybean growth and ozone levels in the US are at its peak. The maps depict ozone exposures calculated for each county in the continental US. The figure on the top is taken from Dr. Tong's 2007 paper showing exposures for 2005. The figure on the bottom shows preliminary results for 2019 exposures using a similar metric, AOT 40. It is important to note that air quality in the Midwest and eastern regions of the US has changed. The air is much cleaner. Most of the heightened exposures in 2019 are associated with the southwestern regions in Southern California, where soybean crops are not typically grown. Soon, I will investigate the ozone data for 2020 and see if differences in air quality brought about by the COVID-19 shutdown will elevate ozone exposures in these Midwestern regions. Then I will be able to determine if soybean crop yields for 2020 are in fact going to be affected.
So another cool application is to use satellite data, in this case from MODIS or VIIRS, to study dust or soil erosion. Soil erosion is caused by turbulent wind lifting soil particles into the atmosphere, and this can have large effects on weather, climate, and also on human health. Soil erosion typically occurs over desert regions which have a high albedo and low vegetation. So using this knowledge, we can map the locations in which soil erosion is more likely to occur, which can be seen in the figure in the top right. Warmer colors, such as over the Saharan desert, show areas that are more likely to undergo soil erosion. But this doesn't just change in space, it also changes in time. In the bottom right, I show the deviation from the average erodibility in time, represented by warming stripes. We can see that not only does soil erosion change seasonally, it also changes interannually.
Hi, I'm Yunya Li. My research focuses on wildfire emission and modeling. Prediction of air quality effects from biomass burning emission is challenging. So we built an ensemble forecast system to reduce the forecast uncertainty. In this system, we include the fire emission products from 4 different institutes. Furthermore, we include 2 polymerized schemes and meteorology outputs from 4 widely used models. Also, we tried different options related to pollution transport. Totally, we have 112 Ensemble members. In order to do investigation, we developed an evaluation system based on the correlation, bias, the overlap of the polluted area, and the concentration distribution differences between the observation and simulation. Here, I want to show an example result for the 2018 campfire. In this figure, red line is observed downwind pollution. Blue line are the results for all Ensemble members, and the black line is the Ensemble mean. Based on our evaluation, the Ensemble mean displayed the best performance. In addition, we developed an ensemble size reduction technique that can save calculation time while improving the performance. In the future, we will try to include more preliminary schemes and model options in the Ensemble system. We also plan to apply this Ensemble forecast method to other hazardous air quality events.
In May 2018, the Kilauea volcano erupted on the Big Island of Hawaii. The HAQAST team received a lot of requests to provide information related to air quality, public health, and emergency responses. At that time, the volcano eruption information was not included in the National Air Quality Forecasting Model. We used the SO2 product from the OMPS sensor aboard the SOMI MPP satellite to estimate SO2 emissions from the Kilauea eruption. With this new satellite-based SO2 approach, we were able to capture the plume of the volcanic fog or VOG downstream in the forecast model. Besides our core project, we have led or contributed to several tiger teams. In 2017, I have co-led a tiger team with broader peers to improve LAX emissions. We also contributed to 6 tiger teams led by Arlene Field, Brian Duncan, Jason West, Patrick Kinney, Susan Annenberg, and Susan O'Neill. Through those collaborative projects, we were able to work with many HAQAST researchers and stakeholders at the international, federal, and state and local levels. A great experience for us. Thanks to LASA for the 4-year support, we were able to develop a suite of emission data simulation packages to improve emissions and air quality forecasting for NO2, SO2, dust, and wildfires. One package, the dust forecasting, is being used by the National Weather Service in their operational forecasting. 2 more packages are being evaluated at an experimental stage, which is the final stage before being promoted to operations, if the performance can beat the current operational system. Through our core and tiger team projects, we had the opportunity to work with many stakeholders, including WMO and the Pan American Health Organization. We also worked closely with NOAA, CDC, EPA, and USDA, and many state and local agencies. Our team has published 24 peer-reviewed papers and gave more than 50 presentations to professional conferences or to the general public. Our research was covered by 29 media reports and 1 award-winning documentary, The Dust Rising by Noreen Schwarzman. The documentary was shown in many events, including the 2019 Environmental Field Festival in Washington, D.C. Thank you for your attention to our work and that of the HAQAST team. Please stay safe and healthy.